computer. Yeah. So first of all, students still ask me about this this problem, which is maybe not so difficult, but this is it's a kind of go back to complex analysis problem. I think 3, 2, 1, where we should integrate over triangle. This is good to study it again. It was at one lecture, but now we study it in general framework if it would be on exam. So there will be 3 points. For example, this point and this point, P1, P2, P3, and there is straight lines. Typically, we consider counterclockwise. We know coordinates of points. PG has coordinates XG, YG. Now, there was a combination of two problems in this exercise. First of all, it was integral over triangle, and here was some exponent z plus z star or minus, it's just dz. Of course, I was shocked that some students, I think today they already know that integral of this function is 0 over any contour. Because on exam, it could be the problem that I write you some very complex contour and some function, for example, cosinus z square multiplied e z8 plus 1 dz. So you need not parameterize this contour. You need not write equations of all these lines. You just know that function is analytic, integral is 0. Yeah, so automatically just 0. So you can forget about this. Integral of this is 0. It's you need not pay attention. Is it triangle or who is this? So finally we are with this problem. Forget about minus integral over some triangle z bar dz. As we studied in some lecture, z bar is not analytic, so this integral is non-zero. And here you should work to calculate this integral. How we do this? We should parameterize all blocks from P1 to P2, from P2 to P3, and from P3 to P1. It may take some time. So it is, this exercise also it is, if you now understand everything is simple, but it may take some time. So what is the first? This is the straight line which go from P1 to P2. And we have here coordinates of this x1, say x2, here x3. And somewhere in gymnasium, at least in now my daughter studied this or course 9, they can write the equation of straight line. So P1, P2, it would have equation y, k, this it would be k1, 2, some coefficient x plus m1, 2. The same you can write equation here and here. How to find equation of straight line connecting 2 points? You have first point, P1, coordinates x1, y1. Put them here. It's one equation. You have second point, x2, y2. Put them here. You have second equation. Finally, you have the system of 2 linear equations with 2 unknown variables, q1, 2 and m1, 2. And you can solve them and find this equation. So you put these points, it would be system of 2 equations. You solve them, and from this system you find k1, 2 and m1, 2. So in school they can do this. So you did this. It was school part of the problem. just for this part. You can do this 3 times. But the systems are very simple. You solve them very quickly. And now you should write dz. You should write z. You should select parameterization. Parameterization can be selected in many ways. It is not once. In this example, they try to select simplest parameterization to make parameter t from 0 to 1. Generally, you don't need this. It would be just integral, not from 0 to 1, but integral from... So my suggestion, always use the most natural parameterization from x1 to x2. So now z is equal on this line, x plus I, y, and now I put y. So z is equal, now I select everybody with x. In front of x, I have 1 plus I k1 to x. And it's also coefficient m1, 2. It's you natural select x as parameterization parameter, which goes from x2 to x1. What they did in this solution, they selected the length of interval x2 minus x1, and they wrote parameterization which has the form x is equal x2 minus x1 t, and now t goes or x1 plus x1, I think, plus x1. When t is 0, we have x1. When t is 1, we have x2. So they use this parameterization. But in principle, you are fine. Just consider as t just x. Just x. Now, if we select this simple parameterization, we can find dz. Dz would be just these coefficients, 1i k1 to dx. And we can find z bar. It would be, who will be z bar? I missed, we should multiply whole y by I, yeah? So I multiplied only this, but I should also multiply this by I, yeah? So here is also I. In dz it's disappear in any event, and then bar is equal 1 minus I k1 2 x minus em1 2. Now I put this into integral and this into integral, and finally for the first, just for the first segment, we get the following integral. Integral from P1 over P2 from this segment. Here we have z. It would be this 1 minus ek1 2 x minus em1 2, and dz is this number, just number 1 plus k1 2 dx. And how we can directly write from x1 to x2. So this is integral, it is linear integral. It is, you can integrate very quickly. These numbers would give you 1 plus k1 2 square. Multiplication, these are conjugate k1 2 square. And you'll get some answer. Then you go to the second, to the third, and you will get the answer. So the sum of 3 integrals. It takes time. Now maybe to simplify, I would make something similar what was in this. Was minus 4, 0, and here was I don't know, for example, 1. Then here equations are very simple. The equation, for example, of this. Here we have x goes less or equal 0, minus 4, and here y is equal 0, so z is equal just, here is no complexity at all, so z is equal just x. Z is equal x, and x is from -1 to 0, if we go this direction. On this line, it is also simple. Here on this line, which we go up, x is equal 0. So it is more natural to select y as parameterization. That so y is between 1 and 0, and z is equal I y. So dz is equal I dy. So parameterization is depend for your convenience. Here it is useful to select x, here is y, but generally it's natural from x1 to x2. For example, if we be here, also there is some another delicate point that when you go from P2 to P3, you go from your x is changed between x2 and x3. So it is not x, not we integrate not from, integral would be not from x2 to, it's okay, integral would be this one, not from x3 to x2, but from x2 to x3. They have different signs, yeah? So control also in which direction you go. Here it would be also integral from x3 to x1, because you go in this direction. Yeah, so this is this example, and I suggest you to train, for example, at home, train with 3 points, yeah? So point, for example, 1, 1, P2 is equal 2, 1, or 2, 3, and P3, maybe my points will be better and select your own good points, yeah? So for example, -1, 2. I hope that no points are on the same line. Yeah, and for example, this function or integral z bar square dz. So this one. So there's no great idea beside of that if you have analytic function, it might be such problem on exam. I will give you very complicated contour and very complicated function. And then you just write it as 0 because function is analytic. But for triangle, it's good training for parameterization. Good training for parameterization. Okay, I hope that it's finally we finished with this problem. It is good. First, I did not pay attention that it can be a problem for you. But you have two problems. First, you have never parameterized something. So, with this one. And second, maybe for you was problem to write equation of this line. And third, yeah, okay, so try to train at home, and then if it does not work, write me again. Now we destroyed this. And one remark which was yesterday about terminology. About terminology. We introduced the notion of Euclidean space. Euclidean space is a vector space with a scalar product. And Hilbert space is a complete means that any Cauchy sequence has limit in this space. It's a complete Euclidean space. This is our terminology. As was rightly remarked in some books, Euclidean space is restricted to finite dimensional. So in some books, when people use terminology Euclidean space, they restrict it to, in the course of linear algebra and so on, to finite dimensional. Then such infinite, this space can be, our Euclidean space can be both finite or infinite dimensional. So for example, it can be Fn, or it can be L2, which is the space of infinite sequences with infinite bases. So our Euclidean space is not finite dimensional. In those books where they restrict Euclidean space to finite dimensional, general linear space with scalar product, which may be not complete, is called pre-Hilbert space. Pre-Hilbert space. So what we call Euclidean space in some books is called pre-Hilbert space, and Euclidean space is reserved only for this. Just if you meet the words pre-Hilbert space, just identify with this. But in our course of functional analysis, which we follow one of the textbooks, it would be Euclidean as we define it now. As we define it now. Okay, in principle, we should also do this everything over complex numbers. We shall do this a bit later. But now what we do? Let us go back what we did last lecture, what we approached. We approached the notion of Fourier series, Parseval equality, and let us recall them. Let us recall them and try to consider example, a kind of exercise. So let H be a Hilbert space, and let En be an orthonormal basis then for any f belonging H, we have Parseval equality. So square of the norm is equal. Here are coefficients Fn square. And coefficients, these Fourier coefficients, they can be calculated F(En). Fourier coefficients. Fourier coefficients for this basis En. The same function can be expanded with respect to different bases, and of course in each basis you have your own Fourier coefficients. In each basis you have your own Fourier coefficients. Now each f can be represented as the sum Fn En, where series converge in the Hilbert space. Convergence in H. Convergence in H. Convergence in H. What does it mean, this convergence? This convergence means that if we take the norm f minus partial sum, as for any series, as in your course of analysis, but instead of absolute value, there is norm. So this should go to 0. This should go to 0. Yeah. So this was abstract theory. Now we go to very special Hilbert space. We go to very special Hilbert space and to very special basis in this space. So we select as H L2 minus pi pi. And as basis En, we select one. The constant is normalized by 2 pi, and cosinus nx by square root of pi, and sinus nx also by square root of pi. Yeah. So this basis. Now any function we can expand with respect to this basis of this space. And this expansion is usual Fourier series, which people study in course of functional of I can say classical Fourier series. Classical Fourier series. So typically in classical Fourier series analysis, they don't want to play with this normalization constants, and they write it in this way: sinus n from 1 to infinity, an cosinus nx plus bn sinus nx. So to get basis, we should divide by square root of pi and include square root of pi in coefficient an. Now, how to calculate these coefficients? How to calculate these coefficients? We wrote the formulas. An is equal 1 over pi integral from minus pi fx cosinus nx dx. Bn is the same with this. And A0, it is normalization by 2 pi. A0, it's 1 over 2 pi. And here is multiplication by 1, so it is just integral of our function, dx. So this is Fourier series. Now we can write how Parseval equality. We can write, so these are formulas, and this also would be a part of examination. There always would be some function, and you should write this Fourier series. So, you can just memorize these formulas, or just remember that it is a basis. In our space. Now, if we integrate, if we try to write Parseval equality for this, we should take into account that the square of the norm of cosinus and sinus, it's not 1 but pi, and for this 2 pi, Yeah. Okay, so let us now solve some examples. What does it mean convergence? What does it mean this convergence? We tell that fx is represented by its Fourier series. In what sense this series converge? It's converged in this space. And what would be this formula in this space? It would be the following. Convergence in L2 space means that this series converge in very special ways. So we have the integral from minus pi to pi. Here we have fx minus minus partial sum of this series. So A0 plus sum n from 1 to n an cosinus nx plus bn sinus nx, yeah, square dx, and this go to 0 and go to infinity. So convergence in this space means only this. If we take integral, and if we average and take the partial sum, and if we average square of the difference, it should go to 0. What is physical meaning of this convergence? We approximate the energy of this signal by energy of this part of our Fourier series. Typically, each n is a channel. For example, in wireless communication, n is just frequency. And we see how the total energy of signal is approximated by energies of signals, on these frequencies. Maybe I write Parseval equality, and Parseval equality is more or less the most important exhibition of energy balance. Yeah. So Parseval equality would be the norm f square, which is integral. So this is the total energy of signal. Signals are always complex valued, so we should soon come to complex numbers, but it would be more or less the same. And this is equal. Now, if we integrate the another part square, so we took 2 pi a0, and here would be the sum n from 1 to infinity. Here, each square the norm of this is pi, so it would be, maybe here it's easy to write pi, and here will be an square plus bn square. Now maybe it's good to normalize by pi, and it will be 1 over pi, from minus pi to pi, f square x dx is equal 2a0 and plus this sum. Now, how people do this in engineering? How they apply this formula in engineering? It is clear that signal is not uniformly distributed in all frequencies. So when you expand this signal into Fourier series and look here, you typically see that for some n 0, n0, this an0, bn0, or for some ng, for some selection of frequencies, these are essentially less than others. So this means that your signal is concentrated on some selection of G1, Gk, on some selection of frequencies. And what typically do people in engineering? They just cut all other frequencies and leave these basic frequencies. Then your signal would be just finite sum. Your signal would be reduced to just the sum over G, A0 plus K is A and G plus B and G is cosinus and G, say sinus and G, G from 1 to K. So the series disappear, and typically, of course, in engineering, they operate with finite sums and finite. Very often, your signal is concentrated is just on one frequency, So in this way, it's typically based on this, when you would like to find some object, and this object may be send signals on some frequency, you make its Fourier series and look which coefficients are largest. Then you understand that your message is going on this frequency, and you can ignore all other frequencies. You can ignore all other frequencies. So expansion, the main application of Fourier series, at least in wireless communication, radio location, and so on, is that this Parseval equality, interpretation of integral of square of signal as energy, and the possibility to select frequencies, at which our signal is the strongest. This is used in compression of information. For example, you want to send this signal, but you don't want to use a lot of channels and information. Then you just make this approximation and send not the whole this signal which contains so many frequencies, but just this block. And typically, if you reconstruct signal, it will be precisely your signal. So the difference between this sum and this block corresponding to the most important frequencies is typically negligible, and very often you use just 1-2 frequencies. So you make huge compression of your signal. You need not send all coefficients or all values of functions and all points, but you send just the most important block of the signal. And people do this, in wireless communication. When they would like to compare two signals, for example, this is complicated signal, another is complicated signal, then they expand them in Fourier series and find the most important coefficients, which are largest, and they see that they are the same. So your signals are practically the same in main frequencies. And how these engineers in wireless interpret other frequencies where these are small? It's typically noise. So around there is a lot of noise. So signal is going on these main frequencies, but it's noised typically from Fx or Gx. You cannot recognize that they are different or they are the same, because noise can destroy everything. Yeah, so this is application of Fourier analysis in engineering. Now let us make some concrete calculation, and I haven't spent some time. Yeah.
I wonder how you got that formula for the square of that integral, square of f.
This is just definition of the norm, да?
Yes, that's one I know.
Then I started to integrate this part. I just here forgot about, we can of course expand with respect to this, and they take into account coefficients. But now I just integrate these parts, yeah? Okay. So if I integrate this, it would be 2 pi. Then these guys are all orthogonal, so I should just integrate square of this. It would be pi. And then I integrate square of sinus, it would be again pi.
Okay, thanks.
So I did not use, so if I would be very careful, I should expand f with respect to this basis. And then, because these coefficients are not Fourier coefficients. No, we don't consider them as normalized, yeah? To get Fourier, we should write here, and then this would be Fourier coefficient in our orthonormal basis. But here, the theory of Fourier series in Hilbert space has some collision with classical Fourier analysis, where they did not consider L2 norm and did not consider normalization. Okay, example. We want to consider some example. Of course, in engineering, they never calculate these coefficients because they are programs, and you just put fx. and you get its spectrum. These coefficients are called spectrum of signal. So the collection of these coefficients, A0, AN, BN, is signals now spectrum. Signal spectrum in energy domain. Okay, so I made at home some exercise, which is also useful to show the power of this Fourier series, not only in engineering, but also in pure mathematics. So many very important things in pure mathematics people got from Fourier analysis. Now we want to prove Euler equality. We write the title. Euler. Euler equality. Yes, Euler equality. No, but for the moment, we don't think about Euler equality, and we want to solve the simplest problem. We have function fx, which is just x, in the segment pi minus pi. And we want to expand this function into Fourier series. This is very good place to discuss one, before make calculations, discuss one property. For example, this function x, it has such property, f minus x equal minus 6. So the graph of this function, pi minus pi, and here we have this point. And if you go in the point minus x and point x, the signs are different. So let us, or it's better write even in this way. Yes. So this function has this property. If we change the sign of argument, the sign of function is changed. Functions which satisfy this equality are called odd functions. And functions which satisfy this equality, f minus x equal fx, even functions. No, for example, who is also beside of x is odd function. For example, sinus nx is odd. Cosinus nx is even. Cosinus nx is even. It does not change sign. Now we want also study such properties of this function. Suppose we multiply two odd functions, f1 and f2 are odd. And now consider function phi, which is the product. Then consider phi minus x is f1 minus 6, f2 minus 6 minus, it is phi x. So the product of two odd functions is even. Even function. Of course, the product of two even functions is even, yeah? The sign is not changed. If you multiply them, sign is not changed. If you now multiply even function by odd function, so it would be odd function. Even function multiplied by odd. This does not change sign, this change, so it is odd. Such properties. Such properties. Why we interested in this classification? Not of course there exist functions which are neither odd nor even, yeah, neither odd nor even. Why we interested in this? Because if we know from the beginning this function, for example, even or function odd, in fact we need not calculate all Fourier coefficients. Some of them are zeros. Some of them are zeros. So, for example, this function is even, or is odd, and in principle, we need not maybe calculate all coefficients. So now general case, so let f x be an arbitrary odd function. Then, for example, its coefficient an for cosinus. It is 1 over pi integral minus pi fx cosinus nx dx. So this function, odd function multiplied by even, it is also odd function. Now consider arbitrary odd function, let f be an odd function. We forgot about trigonometry, and just consider integral from minus pi to pi fx dx. We split this integral into two, one from minus pi to 0, another from 0 to pi, and use this property. So this integral is 0. No, you can just do this, what I told. Split this interval to two intervals from 0 to pi, from minus pi to 0. And on the second interval, make the change of variable x minus 6 and use this property. So this integral is 0. So if function is odd function, all cosinus Fourier coefficients are 0. So an 0 for any odd function. In particular, in our example, for fx equal x, in particular, for fx equal x, an are 0 for any n, including k0. To complete this, let us consider integral of even function. So if you consider, so not from even, but consider this situation when fx arbitrary even function. In the same way, we get all bn is equal to 0. So if fx is equal, if f minus 6 is equal fx, then if you multiply it by sinus, it's become odd function. So or bn are 0. So even function is expanded with respect to cosinuses, and odd function is expanded with respect to sinuses. So maybe we even write this as mini theorem, mini theorem. Let f be an odd function, then its Fourier series is equal O a n is 0, just n from 1 to infinity, bn sinus nx, no cosinus. Let f be an even function, then it's expanded in Fourier series with respect to only cosinuses. An cosinus nx plus a0. So this, no, these even or odd functions can be very complicated, and if you try to calculate Fourier coefficients, directly, it can be very difficult. No, for example, take function cosinus x square fx. Cosinus x4, for example. If you try to calculate Fourier coefficient, you will get integrals, but other integrals are not simple. Yeah, so it's not a good example. I thought that you can just totally eliminate difficult, but this function is even, of course, but coefficients for cosinuses you should still calculate. Okay. So this is mini theorem. Now we know notion even and odd function. Know that for one trigonometric series is just sinus series. For another cosinus. Now we go back to Euler formula and to our function fx. Yeah. To our function fx, which is even function. So it would be this series. We need to calculate only coefficients bn. So bn, this is no more deep things, it's just this integral from minus pi to pi, x sinus nx dx, sinus nx dx. You calculated this integral somewhere in your course of mathematical analysis, and it's calculated by integration by parts. So path integration. So you put sinus into differential, and then integration by parts, you get the answer. And I just did this at home. Its answer would be, after integration by parts, it would be minus 2 divided by n cosinus n pi. So this is my answer. And this n pi cosinus, we know this cosinus of 2pk is 1, and cosinus of odd number of pi is minus 1. So it is equal minus 2 divided by n for n equal to k. And another sign, 2 divided by n for n equal to k plus 1. So this is just calculation of integrals, nothing more. Calculation of integrals. Okay, so since we calculated integral, we can write expansion of x, our function is x, into series. It would be 2 sum n from 1 to infinity. Here I play with this sign, n plus 1 divided by n sinus nx. So this is the first part of the problem. The problem of usual exercises. Maybe today I will send you exercises to expand different functions into Fourier series. This is very simple function x, and we expanded it into this Fourier series. Now Now we would like to use Parseval equality. So for this aim, since we want to use Parseval equality, we would like to calculate the norm of the function. The norm of the function. So.
Question. So when is the derivative that question? The one Bn equal to 1 divided by B.
In the last formula.
No, the first one.
This one.
No, the one above.
This one.
Yeah.
This is just definition of Bn.
But it was only x, then you multiply it by sine x.
Huh?
It was only x,
The role of f is played x in our case, fx is equal x.
okay, and sine x.
Huh?
And sine and x.
It's the definition of coefficient
Oh.
b, and it's just definition of b coefficient. Yeah, now we want the square of the norm. We want the square of the norm. Let us do this. So x square, it is integral from minus pi to pi x square dx, x square dx. So it will be x cube. So 2/3 p cube. So it's not p cube. Now I want to come to at this lecture I already wrote you Parseval without normalizations, but okay, so maybe we shall at home I did normalizations for coefficients okay, we shall do this usual Parseval, yeah. Yeah. At home I was so careful that I made normalization, and then x is equal. I want to divide by, yeah, I want to make here normalization by the square root of pi. Yeah, then it would be en, it would be normalized vector, but if I multiply, I divide it by square root of pi, I multiply. Yeah, so this formula. Now it is x. Now it's usual Parseval with respect to the orthonormal basis, because now this en is orthonormal basis. So now I can write this Fourier. I can write this Fourier equality. No, not Fourier Parseval equality, and it looks so: norm x square. It is equal sum of squares of coefficients. Yeah, coefficients, Fourier coefficients are this and this. So we should square them. In another part would be square of this. It is 4 pi. And here would be sum n from 1 to infinity 1 over n square. Yeah. I just wrote Parseval equality with respect to orthonormal basis En. With respect to the orthonormal basis En. But I also know who is x square. So it is 2/3 p cube equal 4 pi sum n 1 to infinity 1 over n square. Now I would like to find the sum of this series 1 over n square. So, and this is Euler formula. 1 over n square is equal to disappear to 1 pi disappear p square, and we get formula p square divided by 6. P square divided by 6. This formula was very famous because before Fourier series it was very deep number theoretical consideration of Euler. He did not prove it in this way. He proved this: the sum of 1 over n square is p square divided by 6. So to whom I will send you one similar problem. And you will just repeat all this, and you will find the sum of another. I think I don't remember, maybe 1 over n in the degree 4. But machinery is the same. Parseval equality, expansion into the Fourier series. So what time is it now? Is it time for break or not? It's not clear. Yeah, it's time for break. Yeah, we stop recording. 15 minutes break, yeah. Yeah. First of all, as was remarked, there was misprint in the Bessel equality for function f. So we wrote that 1 over pi integral x dx is equal. And here was, I don't want to write everything, a 0 plus and so on. But it's clear that it's wrong. That just as was remarked just by dimension, because a n square, b n square, so it also should be square. So just correcting this formula, go to the previous. Here was this sum. And here I wrote a0 without square. So e square to a0. That was misprint. Okay, so now we would like to go to complex Fourier series. And what is, write this title. We write this title. Complex Fourier series. And we again go through, Hilbert space formalism. First of all, we need normal space over complex numbers. Quite quickly write everything which was written for real numbers, for complex numbers. Let, for example, x be a complex linear space. Or vector space. So vectors can be multiple. The role of scalars is played by complex numbers, not by real. So we can write linear combination C1 or U plus C2 U1, C2 U2, where C1, C2 are complex numbers, and vectors U1, U is equal to are vectors of our space. So we can write combinations of vectors with complex coefficients. It is not easy to visualize complex linear space because already two-dimensional complex linear space, it's four-dimensional real space. Yes, there are two real parameters, and yeah, so okay, so now norm. We have the notion of the norm, and it is the same besides just one property. One property of the norm should be corrected. What property is different, we illustrate by example. As the basic example, take Cartesian product of complex numbers. Yeah, Cartesian product of complex numbers and vectors. The 1, 2, the n. And on this space, let us introduce the norm. For example, as we introduce the norm 1, it was the sum k from 1 to n, zk, and here is complex absolute value. So the only difference that you now, instead of usual absolute value, take complex absolute value. Now, in this example, let us multiply z by lambda. And lambda is also complex. So, and it would be k from 1 to n lambda zk. And now lambda is complex scalar product, complex absolute value, so it is product. And here is complex absolute value of lambda, and this sum is again the norm. Yeah. So it is, in fact, formally it's the same formula, but absolute value is complex. So in the definition of norm, we have the following equality: lambda z is equal lambda z that belongs to x, lambda to complex, and lambda is complex absolute value. So the only difference, if we multiply vector by scalar and take the norm, the scalar can be taken away with, of course, with complex absolute value. What can be other way? Yeah, so complex linear space with norm. So this is complex normed space. Complex normed space. When the norm has this property, complex normed space. Now go to complex Euclidean space. It's again, okay. So it is again a complex linear space. We modify definition of scalar product. We modify the definition of a scalar product. Again, we start with this example, Cn, but here we introduce the scalar product of two vectors, z, w. If you write in this way, k from 1 to n, zk, wk, then if you multiply z by z, it would be z square, it would be not positive. To make positive, we use that if you multiply z star, it is z square, so it is non-negative. So we should put here bar. Oh no, bar it's in our so, complex conjugate. If you put here complex conjugate, then we see that if you put here complex conjugate, we see that z by z, it is sum k from 1 to n zk. So it is non-negative. It is non-negative. This example, if we put here the sum of 2z, then will be the sum of the coordinates. So it is clear that if you put here z plus, for example, u, w, we can open the brackets. So it would be z, w plus u, w. If you put in this example lambda here, it would be lambda here. It is go out just as usual lambda. So multiplying by lambda first coordinate, lambda z w, it is the same lambda z w. So in this example, scalar product is linear with respect to the second argument. Is linear with respect to the second argument. Oh, the first argument, is linear with respect to the first argument. Why I made such mistake in my statement? Because physicists in the books, if you read the books on quantum mechanics and so on, they use another scalar product. It would be zk wk. So in physics it is complex conjugate for the first coordinate. But in mathematics, they use the as I wrote. complex conjugate of the second coordinate. So, but if you put now linear, if you put now the sum to the second, it's again sum because conjugate to the sum is sum. But now let us put lambda to the second argument. Z lambda W. If you put lambda, it would be lambda WK star. It is equal lambda star WK star. So lambda go out as conjugate. Or right here, ZW. So from the second argument, scalar goes not just as it is, but with complex conjugate. So now we define complex linear product on a linear space. So complex, or one more property which is not the same as for real. For real, we had that xy is equal yx. Real scalar product was symmetric. But here, let us try to change arguments. So this is z w, and let us write wz. It would be sum k from 1 to n. First now wk star, wk zk star. So now how they are related, this one and this one. So no, it's clear that this is not this, so they are not symmetric. They are now related by this two stuff. So if we change variables in the complex scalar product, it would be star in the. So this number would be this complex conjugate. So now these properties. Now let us denote this, for example, this equation 1, this equation 2, and this is equation 3. This is equation 3. So complex scalar product has the properties z non-negative, z equals 0, you can only if z is 0. Second, linear with respect to first argument. Third, sometimes it's called skew linear or Hermitian linear, no, how we call this, conjugate linear, with respect to second argument. So conjugate linear with respect second argument, and skew symmetric. So ZW is equal WZ star. Yeah. So this is complex linear product. Complex scalar product. So the space with complex scalar product is called complex Euclidean space. So E with complex scalar product. Let us give direct definition. E with complex scalar product, which is complete with respect to the norm. We call it a complex Hilbert space. We call it a complex Hilbert space. A complex Hilbert space. So everything is very similar, practically the same as it was for real. We have here also Cauchy-Bunyakovsky-Schwarz inequality. We can prove that this is really norm, but it's done in the same way as it was in the real case. As it was done in the real case. Maybe we can write that here we also have Cauchy-Bunyakovsky-Schwarz, but here this is complex absolute value. And here is square root z norm square root w. So Cauchy-Bunyakovsky-Schwarz inequality. And by using this Cauchy-Bunyakovsky-Schwarz inequality, we can prove that this is really the norm, because this definition does not guarantee that it is a norm. We just thought, oh, this is the norm. But we should prove triangle inequality. To prove triangle inequality, we again need the inequality, Cauchy-Bunyakovsky-Schwarz inequality. And so then it is normed space, then it is metric space. So then it is, we can speak about complete and non-complete. Okay. And as in the real case, we are interested in one just special space of square integrable function. But before this, let us, okay, I will reserve this to the very end. Was one of our very big problems is this course going before the course of Lebesgue integration. So you did not study the theory of real good integration, because Riemann integration is it's too trivial. It does not cover the Hilbert space analysis, but what we can do nothing. Therefore, I have some secrets, and some students discover some my causalties, and because I operate very easily with this dx. Nevertheless, now consider L2 minus, or put here minus pi. You can write complex here, but typically we will not write complex, just have in mind that now we start to consider complex valued functions. So this is function from minus pi to complex numbers, such that square integral minus pi to pi, and here is complex absolute value. That's an infinity. In real case, we wrote just a square. Here we should write complex absolute value. And here we introduce scalar product. If G is integral G star x dx, you can see that it satisfies all properties of complex scalar product. If you multiply second function by lambda, it goes from scalar product with conjugate. It goes from scalar product with conjugate. And now consider in this space such functions Enx, exponent Enx, and n is integer. So n is 0 plus minus 1. Here we go to even to negative n. So consider these functions. Exponents in different degrees nx. Complex exponents. Now let us calculate integrals from minus pi to pi. So write En, Em, scalar product. We would like to prove that they are orthogonal. We would like to prove that they are orthogonal. Which these functions are orthogonal. Now put these functions and make integration. Yeah, so this is E and X, here is this bar, da, minus mx dx. I use H if you take E mx star, it is minus E mx. It was used because our scalar product is this complex conjugate. Our scalar product is this complex conjugate. Okay, so now I collect exponents and just calculate integral. There's nothing special. Ex n minus m dx, and this is equal Ex n minus m divided by I n minus m, and here from minus pi to pi. Now consider our exponent, consider such thing. This is just number, we take it away, consider it's equal, and here we have E pi n minus m minus E pi minus pi n minus m, and divided by this, divided by this number. So we consider two cases, n equal m and n not equal m. Yeah, it's equal. If n is equal m, if n is equal m, no, we would not use this formula. It's we use directly here. Then we integrate just one, because if n is equal m, its exponent in the degree 0, so we integrate just one, so it is 2 pi. So if n is equal m, it is 2 pi. If it is not equal, look, here is exponent. If we make a pi, it is either on real line or on the negative direction. Then we make rotation n minus m times. This is rotation in this direction, and this is rotation in the opposite direction. So we come to the same number. So minus, so if we have, for example, some vector, and we rotate k pi times this direction, for example, once, we arrive here. If we rotate the same number of numbers in this direction, we also come here. So these numbers are the same. So it is 0. And not equal m, it is 0. So they really orthogonal. So they really orthogonal. And moreover, we can, they are not, we should normalize them. They are not yet basis. Huh? They are not yet basis. Because when they equal, we get 2 pi. So when they equal, we get 2 pi. To get orthonormal basis, we have what we prove now, En is equal delta Nm 2 pi. Delta Nm 2 pi. So let us normalize now them by square root of 2 pi and write, for example, En tilde x, which is 1 square root of 2 pi, exponent E n x, or n is integer number. So now we can expand any f in our space. Of course, what we are not doing, and this is a difficult theorem where we also should use Lebesgue integration. we have not done even this in real case. We maybe have another whiteboard. What we did in real case? In real case, we have these functions 1 to pi cosinus nx square root pi and sinus nx square root pi. Let us call this remark. Let us call this remark. We prove that this is orthonormal system. We proved that this is an orthonormal system. But we did not prove that it is a basis. We did not prove that for any f, fx is really equal to this, the sum fn en. This is very difficult theorem. No, not so difficult, but here you should know Hilbert integration. We should show that really any function f can be approximated by these numbers, by this series. So we took this as given. So we did not prove that En is really a basis, or in terminology of other book, is sometimes called complete orthogonal system, orthonormal system. So basis is complete orthonormal system. For example, if you take only sinuses, this is also orthonormal system, but it's not complete. Not every function can be expanded with respect to sinuses. If you take these ones, they are neither complete orthonormal system. So in the same way, when we go to this complex case, we know that this system is orthonormal. But again, we just take as given that it is basis. So we don't prove that En tilde is really a basis. But we use this. We expand any function with respect to this, but it is not proved. In principle, it can happen that we can write function, we can write its Fourier series, and in principle, the difference may be not zero. Yeah, so this is, yeah. So now in any event, we assume that we know that this is basis, and then we can expand again any function with respect to this complex basis. We can expand any function with respect to this complex basis. Again, people don't want to play with this normalization, and they just write fx sum n from minus infinity to plus infinity. Here are Cn, Enx. And if you want to write Parseval equality, it would be integral of f squared. So it is integral from minus pi to pi fx squared dx, and it would be equal sum n from minus to plus Cn squared and the square of the norm, nx square, we calculated 2 pi. So it would be 2 pi. So we will get this formula 1 over 2 pi integral from minus pi to pi fx square. It is equal to the sum minus infinity plus infinity cn square. So this is complex form of Parseval equality for trigonometry for Fourier series, So this is complex form of Parseval equality for Fourier series. And if those who use in signal analysis, they always work with complex amplitudes, and they always use this Fourier expansion, not through, some use cosinus and sinus, and yeah. Sometimes it's better complex, sometimes real. It depends on your problem. Again, these are frequencies, and you select the largest coefficient, and this is more or less where your signal is concentrated. So you cut off everything in this series, but only select those who are big. And for example, if you want to compress signal, or if you want to, for example, if you work on image recognition from satellite, you are looking to some object, and you expand the signal from this object in this Fourier series. And of course, there is a lot of noise, maybe also some forest and so on. But you want this object. Typically, object is precisely on these big frequencies. Then you take away everything beside those big frequencies, consider only the sum for big frequencies, and you will see the picture of this object. So it's work. Oh, of course, now these are computers who do this. Yeah, it's enough for today. And I did not even start to prove this very big theorem, which maybe we do next Monday. And today I will send you maybe home task on Fourier series or tomorrow. Yeah. Okay.